So today we're going to do a three-dimensional trigonometry word problem. It's actually question 6 in chapter 5.8 in the Nelson grade 11 functions textbook. So let's get started. The observation deck of the Skylon Tower in Niagara Falls, Ontario is 166 meters above the Niagara River. A tourist in the observation deck notices two boats on the water. From the tourist's position, the bearing of boat A is 180 degrees at an angle of depression of 40 degrees. The bearing of boat B is 250 degrees at an angle of depression of 34 degrees. Calculate the distance between the two boats to the nearest meter. So the first thing you're going to want to do is draw a diagram to get some sort of visual representation of the problem. So I'm just going to draw the water. So this is the river, and we know the Skylon Tower is 166 meters above the river. So I'm just going to draw that tower, and it's 166 meters above the water. And we know that the deck is at the top, so the person is also at the top. So now we need to figure out where the boats are with respect to the person, and we can do that by using the bearings. And the bearing for boat A is 180 degrees, so let's just ignore the angle of depression for now. To get the position of the boats, you just need to draw this from a bird's eye view. So this is going to be the Skylon Tower, and this is going to be the person's head. And we're going to draw north, east, south, west. So to get the position of the boats, you just start at north, which is 0 degrees, and go clockwise until you reach your bearing. So it would be 90 degrees at east, 180 at south, 270 at west, and back to 0 at north. So the bearing for boat A is 180 degrees, so we know that boat A is going to be here, directly in front of the person. And we can put that in our other diagram as well. Now boat B has a bearing of 250 degrees. If you start at 0 here and go to east 90, south 180, west 270, that's a bit too far, so we're going to go back around here, so 250. We can draw boat B in our other diagram as well. Now when you're calculating the distance between the two boats, you're looking for the shortest distance, and the shortest distance is always going to be a straight line. So you're looking for this distance right here, and we'll call this distance D. Now I just added two lines connecting the top of the tower to each of the two boats. So if I were to draw this again more simplistically, we would have a triangular based pyramid where we have boat A here, boat B here, and the distance between them here. And we have the top of the tower here, which we'll call C. And we already know this length here because this is the height of the tower, and the height of the tower is 166 meters. Now to solve for this distance D, we're going to need a bit more information. It is one of the side lengths of the base of this pyramid. We can solve for this angle here by using our bearings. So imagine we are looking at this from a bird's eye view. The top would just be a point and you'd see the base here. So I'm just going to draw that. So we know that it extends here and it connects B with A. And this is the distance between them, D. Now how do we solve for this angle, or this angle here? From north to south, or point A, that is 180 degrees. From north to B, that is 250 degrees. Now to get that green angle, which is equivalent to this part of the blue angle, we need to subtract 180 from the 250 degrees. So the green angle is equal to 250 degrees minus 180 degrees, which is 70 degrees. So the angle of depression for boat A is 40 degrees from the horizontal at the top of the Skylon Tower to boat A. The angle of depression for boat B is 34 degrees from the horizontal at the top of the Skylon tower to boat B. So you can kind of imagine this like an open book. If you have an open book, it looks somewhat like this. If this is the Skylon tower in the middle here, which is 166 meters, and boat A and B are here, the angles of depression would be the angle here and the angle here, because it is from the horizontal looking down, and depression means down. So you're looking down at boats B and A from the horizontal at the top of the tower. But we don't want these angles because they are not the ones in our diagram. We want the angles in here and here because they represent these angles in our diagram. All you have to do is imagine these are pages in a book. And if these are pages in a book, then these are rectangles, and rectangles have 90-degree corners. So if we know this angle is 40 degrees and this other angle is 34 degrees, then we can find the angles we need. This angle is going to be equal to 90 degrees minus 40 degrees, so 50 degrees. And this other angle is going to be equal to 90 degrees minus 34 degrees, so 56 degrees. Now that we know these angles, we can add them to our other diagram. Since these are both rectangles, these corners are both going to be 90 degrees. So let's add this to our other diagram. I'm going to label this point capital D. So this triangle here on the right is going to be triangle CDB, where this is 90 degrees, this is 56 degrees, and this is 166 meters. We need to figure out this side length that I'm going to call E. There are many ways to solve for the length of E, but I'm going to solve for angle B and then use sine law to solve for E. Since all the interior angles of a triangle add up to 180 degrees, I know that angle B is equal to 180 degrees minus 56 degrees, which is 34 degrees. Now I'm going to do sine law. So the sine of 34 degrees divided by 166 meters is equal to the sine of 56 degrees divided by E. A shortcut for doing cross multiplication to solve for an unknown, like E, is just to multiply your two known values that are opposite to each other, or diagonal, and divide by your remaining known value. So E is going to equal 166 sine 56 degrees divided by sine 34. We're going to keep our values exact until the end, so I'm going to save this for later. And now I'm going to find the other length of the base using the other triangle. So this is triangle CAD. We know that this angle is 90 degrees, this angle is 50 degrees, and this angle is complementary to angle C, so it is 40 degrees. We also know this is 166 meters. So like we did before, I'm going to use sine law and solve for this length here. Let's call it x. So sine 50 degrees over x is equal to sine 40 degrees over 166 meters. So using that same trick again, I'm going to multiply the two known values that are opposite or diagonal to each other and divide that by the remaining known value. So x is going to equal 166 sine 50 degrees divided by sine 40 degrees. And now I'm going to save this for later as well. So now that we know those two values, we can solve for that distance between A and B. I'm just drawing the base from a bird's eye view again. Remember, this is the point D on our diagram, or base of the tower, and this is boat A, boat B, and this is the distance between them. This is the 70-degree angle between them. This is our side length E that we know, and our side length X that we know. With this information, we can solve for D using the cosine law. So that is a squared equals b squared plus c squared minus 2bc cos A. But we didn't use A, B, and C, so we're going to have to substitute that with E, X, and 70. If I were to rewrite this, lowercase letters represent side lengths, and the corresponding uppercase letter would represent the angle opposite to that side length. So the lowercase a is the side length we're trying to figure out. So I'm going to write d squared in its place. And b and c are the other two known side lengths, so e and x. Minus 2, so we made be and cx. Cos, we made lowercase a equal to lowercase d, so uppercase A is the angle opposite to lowercase d, so 70 degrees. So this is the equation we're going to use, and we're going to plug in the exact values for E and X to get the most accurate length D. And when you do that, you get D squared is approximately equal to 66,400.883554 meters. So D is approximately equal to the square root of that, and because it asked for us to round to the nearest meter, the distance between the two boats is 258 meters.